Hello there, gentle souls, and welcome to Whispers of Science, where wonder gets wonderfully quiet and curiosity finds its cozy corner. Tonight, we're painting the sky with one of nature's most breathtaking masterpieces, the rainbow, that shimmering arc of color that appears like magic after a storm, transforming ordinary droplets into something absolutely extraordinary. But before we chase these bands of light across the heavens, I'd love to know where in the world you're listening from, and have you ever paused mid-step when a rainbow suddenly bloomed across your sky? There's something about that moment, isn't there, when the light bends just so, and suddenly the air itself seems to be whispering secrets in 7 different languages. If you find yourself settling into this gentle journey through the science of light and color, I'd be ever so grateful if you gave this video a quiet thumbs up and perhaps subscribed. It helps this little corner of calm reach others who might need a peaceful pause in their day, too. Now, I do hope this exploration is soothing enough to guide you toward rest, but if it happens to keep you awake with wonder, well, at least you'll drift off knowing how sunlight learns to dance. So take a deep breath, let your thoughts slow like settling dust, and let's begin our quiet voyage into the luminous world of rainbows. Rainbows have been enchanting humans since we first looked up at the sky and wondered why sometimes, after the rain, the heavens seem to crack open and spill colored light across the world. Ancient civilizations saw them as bridges between realms, messages from gods or promises painted in the air. The Norse imagined Bifrost, a rainbow bridge connecting Earth to Asgard, while the ancient Greeks believed Iris, the goddess of the rainbow, carried messages between the heavens and the mortal world. There's something deeply human about wanting to touch a rainbow, to reach that shimmering arc and claim its colors for ourselves. Children chase them across fields, convinced that if they run fast enough, they'll find that mythical pot of gold. Adults smile knowingly but still feel that tug of magic when those bands of light appear like nature's own stained glass window suspended in the mist. But what exactly is a rainbow, and why does it appear when it does at its heart? A rainbow is light, having a conversation with water droplets, a gentle negotiation between sunshine and moisture that results in one of the most beautiful optical phenomena our planet has to offer. It's not really an object you can touch or a physical thing hanging in the sky, but rather a pattern of light, an illusion, if you will. Though calling it an illusion seems almost unfair when something brings such genuine joy to anyone who witnesses it. Think of it more as light's way of showing off, revealing colors that were hiding in plain sight all along. The science begins with understanding that what we call white light isn't actually white at all, but rather a mixture of all the colors of the visible spectrum: red, orange, yellow, green, blue, indigo, and violet, all traveling together like a perfectly harmonized choir of wavelengths. This might seem impossible. When you look at sunlight, it appears so clearly white or golden, but those colors are there waiting patiently to be revealed under the right circumstances. Sunlight, it's like a book written in invisible ink, and raindrops are the gentle heat that makes the hidden words appear. When a beam of sunlight encounters a water droplet, something magical happens. The light doesn't simply bounce off or pass through unchanged. Instead, it bends or refracts, as scientists say. This bending occurs because light travels at different speeds through different materials. It moves fastest through the vacuum of space, slows down a bit in air, and slows down even more when it enters water. Imagine light as a marching band walking from pavement onto soft grass. The front row hits the grass first and slows down, while the back row is still marching at full speed on the pavement. This causes the entire formation to turn or bend, and that's essentially what happens when light enters a water droplet. But here's where the story gets even more interesting. Different colors of light bend by different amounts when they enter the water droplet. Red light bends the least, while violet light bends the most. This separation of colors is called dispersion, and it's the key to understanding how rainbows form as the light travels through the droplet. It hits the back surface and reflects like looking in a curved mirror. Then, as it exits the droplet, it bends again, further separating the colors. What started as a single beam of white light emerges as a fan of distinct colors, each following its own slightly different path. Now you might wonder why we see rainbows as arcs rather than straight lines or random patches of color. The answer lies in geometry and perspective. When millions of water droplets are suspended in the air after a rain shower, each droplet acts like a tiny prism, separating light into colors. But you only see the rainbow colors from droplets that are positioned at just the right angle relative to your eye, and the sun specifically. This angle is about 42 degrees for the main rainbow. This creates what's called the rainbow cone, an invisible geometric shape with your eye at the tip and the rainbow forming along the base of the cone. From your perspective, this cone appears as an arc because you're seeing only the portion of the rainbow circle that's above the horizon. If you could somehow position yourself high enough, perhaps in an airplane, you might see a rainbow as a complete circle, a perfect ring of color floating in the sky. This is why rainbows always appear opposite the sun. If the sun is behind you and to your right, the rainbow will be in front of you, and to your left, it's like the sky's own shadow puppet show with light and water droplets as the performers. The size and brightness of a rainbow depend on several factors. The size of the water droplets plays a crucial role. Smaller droplets create brighter, more vivid rainbows with clearly defined color bands. Larger droplets produce dimmer rainbows with colors that blend into each other. The height of the sun also matters. Lower sun angles create taller rainbows, while higher sun angles create smaller arcs. This is why the most spectacular rainbows often appear in the late afternoon or early morning when the sun hangs low in the sky. Sometimes, if you're very fortunate, you might spot a double rainbow, a fainter secondary arc appearing above the primary one. This happens when light undergoes two reflections inside the water droplets instead of just one. The secondary rainbow is always dimmer than the primary one, and its colors appear in reverse order, with red on the inside and violet on the outside between the two rainbows. You might notice a darker band called Alexander's Dark Band, named after Alexander of Aphrodisias, who first described it. This darker region exists because of the way light scatters within the droplets, creating an area where fewer photons reach your eye. There are also more exotic rainbow phenomena that occur under special conditions. Fog bows appear in fog rather than rain and are much fainter and whiter than regular rainbows because fog droplets are much smaller than raindrops. Moonbows or lunar rainbows can appear on bright moonlit nights, though they usually appear white to our eyes because moonlight is too dim to activate our color vision. Strongly supernumerary rainbows show up as faint colored bands inside the primary rainbow caused by interference between light waves. These delicate additional arcs remind us that light behaves not just as particles, but as waves creating patterns of reinforcement and cancellation. The colors we see in rainbows aren't arbitrary but follow a specific order that never changes the sequence. Red, orange, yellow, green, blue, indigo, violet is often remembered by the mnemonic Roy G. Biv, though some modern scientists prefer to simplify it to 6 colors, omitting indigo. The wavelengths of these colors range from red at about 700 nanometers to violet at about 400 nanometers, with each color blending seamlessly into the next. Our eyes and brain interpret these different wavelengths as distinct colors, but in reality, the rainbow is a continuous spectrum with countless subtle gradations. Interestingly, not everyone sees rainbows in exactly the same way. People with color vision differences might perceive the bands differently, and cultural factors can influence how we categorize and name the colors. Some languages have fewer words for colors, while others have more nuanced distinctions. The physical phenomenon remains the same, but our interpretation of it can vary. This reminds us that rainbows exist at the intersection of objective science and subjective experience, where physics meets perception. The story of how we came to understand rainbows scientifically is itself a fascinating journey through human curiosity. Aristotle attempted to explain rainbows in ancient Greece. Though his theories were quite different from our modern understanding, he believed they were reflections of the sun in cloud droplets, which wasn't entirely wrong, but missed the crucial role of refraction. It wasn't until the 17th century that scientists began to piece together the true nature of rainbow formation. The breakthrough came when researchers started experimenting with prisms, triangular pieces of glass that could bend and separate light. Isaac Newton famously used a prism to demonstrate that white light contained all the colors of the spectrum. He showed that these colors could be separated and then recombined back into white light, proving that the colors weren't created by the prism, but were already present in the original light. This was revolutionary thinking at the time, challenging the prevailing belief that prisms somehow added color to light, rather than revealing colors that were already there. René Descartes made significant contributions to rainbow theory by calculating the angles at which light would emerge from water droplets after reflection and refraction. His mathematical approach helped explain why rainbows appear at specific angular distances from the sun and why they maintain their characteristic arc shape. Though Descartes worked out much of the geometry, he couldn't fully explain why we see distinct color bands rather than a continuous blend of light. The complete explanation had to wait for our understanding of light as both a wave and a particle phenomenon. The wave nature of light helps explain some of the more subtle rainbow effects, like supernumerary bows, while the particle nature helps us understand how individual photons interact with water molecules. This dual nature of light, one of the fundamental mysteries of physics, adds another layer of wonder to something as seemingly simple as sunlight dancing through raindrops. Even today, with all our scientific understanding, rainbows retain their ability to surprise us. They appear when atmospheric conditions align in just the right way, creating moments of unexpected beauty that can stop traffic and fill social media feeds with photos that never quite capture the ethereal quality of the real thing. There's something about witnessing a rainbow that feels personal, as if nature has painted this arc of light specifically for you, even though millions of droplets and countless physics calculations have conspired to create this single moment of wonder. But rainbows aren't confined to the sky. After rainstorms, you can create your own miniature rainbow with nothing more than a garden hose on a sunny day. The fine mist from the spray contains countless tiny droplets, each one a potential prism waiting to reveal the hidden colors in sunlight. Position yourself so the sun is behind you and spray the water into the air. And there it is, your own personal rainbow, dancing in the droplets you've created. It's the same physics, playing out on a smaller scale, the same light, bending and separating the same geometry, creating that familiar arc. This brings us to one of the most enchanting aspects of rainbow science: the fact that no two people ever see exactly the same rainbow, because the rainbow depends on your specific position relative to the sun and the water droplets. Your rainbow is unique to you. Your brother standing 3 feet away is seeing light from an entirely different set of droplets, even though you both perceive the same beautiful arc. It's as if each person gets their own private light show, tailored by the universe to their exact coordinates in space and time. The intensity and visibility of rainbows also depend on the background against which they appear. A rainbow against a dark, stormy sky appears far more vivid than one against a bright white cloud. This contrast effect explains why the most memorable rainbows often emerge from dramatic weather, when dark clouds provide the perfect backdrop for nature's light show. It's as if the storm itself is the theater and the rainbow is the grand finale, the moment when chaos resolves into perfect order. Water droplets aren't the only things that can create rainbow effects. Ice crystals in the atmosphere can produce similar phenomena, though with their own unique characteristics. Sundogs, or parhelia, appear as bright spots on either side of the sun, created when sunlight passes through hexagonal ice crystals in high, thin clouds. These aren't true rainbows, but they share the same fundamental principle: light interacting with water in its various forms to create beautiful optical displays. The size of water droplets plays a fascinating role in determining the character of the rainbow. Very small droplets, those found in light mist or fog, create what's called a white rainbow or fog bow. These appear as broad, pale arcs with very little color, because the tiny droplets scatter light differently than larger raindrops. The physics is similar, but the visual result is hauntingly different, like a ghost of a rainbow painted in shades of silver and pearl. Larger droplets create the vivid, colorful rainbows we know and love, but there's a sweet spot in droplet size that produces the most spectacular displays. Droplets that are too large create dim rainbows with muddy colors, while those that are too small wash out the colors entirely. Nature seems to know this sweet spot, intuitively creating conditions after thunderstorms when droplet sizes are just right for maximum rainbow brilliance. The duration of rainbows varies greatly. Some last only seconds, while others persist for nearly an hour. The longest recorded rainbow lasted over 9 hours, appearing over Yorkshire, England, and slowly moving across the sky as weather conditions remain stable. This marathon rainbow reminds us that these phenomena aren't just fleeting moments of beauty, but complex interactions between light and atmosphere that can persist as long as conditions allow. Altitude affects rainbow viewing in interesting ways. The higher you are, the more complete your view of the rainbow's circle. Mountain climbers and airplane passengers sometimes witness spectacular circular rainbows that ground level observers never see. This three-dimensional aspect of rainbows adds another layer to their mystery. What appears as a simple arc from the ground reveals itself as part of a perfect circle when viewed from above. The mathematics behind rainbows involves elegant geometry and wave physics that would make any scientist smile. The primary rainbow appears at an angle of approximately 42 degrees from the antisolar point, the point directly opposite the sun from your perspective, while the secondary rainbow appears at about 51 degrees. These angles are universal constants written into the very nature of light and water, creating a cosmic consistency that spans cultures and centuries. Interference patterns in light waves create some of the more subtle rainbow effects when light waves interact. They can either reinforce each other, creating brighter bands, or cancel each other out, creating darker regions. This wave interference explains the delicate supernumerary bows that sometimes appear as faint colored fringes inside the main rainbow. These ghostly additional arcs are reminders that light behaves in ways that still seem magical even when we understand the physics behind them. The polarization of light in rainbows creates another layer of complexity. Polarized sunglasses can dramatically change how you see a rainbow, sometimes making it appear much more vivid, and other times causing it to nearly disappear. This happens because the light in rainbows becomes partially polarized as it reflects and refracts through the water. Droplets photographers often use polarizing filters to enhance or diminish rainbow effects in their images, playing with this property of light to create more dramatic compositions. Seasonal variations in rainbow frequency occur because of changing weather patterns and sun angles. Spring and summer thunderstorms create ideal conditions for rainbow formation, with their combination of intense sunlight and scattered showers. Winter rainbows are rarer, but often more dramatic, appearing against snow-covered landscapes, where the contrast makes the colors seem almost impossibly vivid. Autumn brings its own rainbow magic, as lower sun angles create larger arcs that seem to embrace the changing foliage. The cultural significance of rainbows extends far beyond their scientific explanation. They appear in creation, myths, religious texts, and folklore from virtually every human civilization. This universal appeal suggests something profound about how we respond to these displays of natural beauty. Perhaps it's the way rainbows appear suddenly and unpredictably like gifts from the sky. Or perhaps it's their ephemeral nature, reminding us to pause and appreciate moments of wonder before they fade away. Studying rainbows scientifically has revealed layers of complexity that make them even more wondrous. The simple act of sunlight meeting water becomes a symphony of physics, where wavelengths dance and angles conspire to create beauty. But perhaps the most remarkable discovery is that rainbows exist in a space between the real and the imagined. They're not objects you can approach or structures you can measure with a ruler, yet they follow precise mathematical laws that govern their appearance with absolute consistency. The relationship between observer and rainbow is unlike almost any other natural phenomenon. Move a few steps to the left, and you're seeing an entirely different rainbow created by different droplets at different angles. It's as if nature has created a personal light show for each viewer, a private conversation between you and the sky that changes subtly with every breath. You take this intimate quality helps explain why rainbows feel so magical, why they seem to speak directly to something deep within us. The speed at which rainbows can appear and disappear adds to their mystique one moment. The sky is ordinary gray clouds and steady rain. The next moment, the sun breaks through, and suddenly there it is a perfect arc of color spanning the heavens, as if someone has just switched on the most magnificent neon sign in the universe. Then clouds shift the angle changes, and it's gone, leaving only the memory and perhaps a photograph that never quite captures what your eyes witnessed. Modern technology has allowed us to study rainbows in ways our ancestors never could. High speed cameras can capture the formation of individual droplets and track how they interact with light spectrometers, can analyze the exact wavelengths present in different parts of the rainbow, and computer models can predict when and where rainbows will appear with remarkable accuracy. Yet all this scientific precision somehow enhances rather than diminishes the wonder we feel when we see one. The discovery that rainbows follow mathematical principles led to some of the earliest advances in optics and our understanding of light itself. Scientists studying rainbows helped develop theories about refraction, reflection, and the nature of color that would later be applied to telescopes, microscopes, and countless other optical instruments. In a very real sense, our modern understanding of light began with people wondering why the sky sometimes painted itself in colored bands after storms. Atmospheric scientists have identified dozens of rainbow variants, each with its own specific formation conditions. There are reflection rainbows that appear over bodies of water, creating the illusion of rainbows, extending both above and below the horizon. Twinned rainbows where two separate arcs emerge from the same cloud system, and even red rainbows that appear just after sunrise or before sunset when blue light has been scattered away by the atmosphere, leaving only the warmer colors to paint their arcs across the sky. The physics of rainbow formation connects to broader principles that govern how we see the world around us. The same refraction that creates rainbows also makes swimming pools appear shallower than they really are and causes mirages to shimmer on hot desert roads. The scattering of light that separates rainbow colors is also responsible for blue skies and red sunsets, connecting these everyday phenomena to the more spectacular displays we see after storms. Droplet size distribution within rain clouds creates subtle variations in rainbow appearance that meteorologists can read like signatures. Different types of precipitation produce different rainbow characteristics. Light drizzle creates one type of rainbow, while heavy downpours create another, and the transition between different precipitation types can cause rainbows to shift and change in real time. As you watch, this dynamic quality reminds us that rainbows are not static displays, but living interactions between light and atmosphere. The energy carried by rainbow light is the same energy that drives photosynthesis, feeds solar panels, and warms our skin on sunny days. The colors we see separated in rainbow bands are the same wavelengths that plants use to grow and that our eyes evolved to detect. There's something poetic about the fact that the light that creates rainbows is also the light that makes life on Earth possible, connecting these beautiful displays to the fundamental processes that sustain our planet. Scientists have discovered that the angle at which you see a rainbow encodes information about the size of the water droplets creating it. Experienced meteorologists can estimate rainfall intensity and droplet distribution just by observing the characteristics of a rainbow. This means that rainbows aren't just beautiful, they're also informative, carrying encoded messages about atmospheric conditions for those who know how to read them. The study of rainbows has practical applications that extend far beyond satisfying curiosity. Understanding how light interacts with water droplets helps engineers design better spray systems for agriculture irrigation and fire suppression. The same principles that create rainbows are used to develop optical instruments, medical devices, and communication systems, showing how basic research into natural phenomena often leads to unexpected technological advances. Polarization effects in rainbow light create patterns that some animals can see, but humans cannot. Many insects and birds have visual systems sensitive to polarized light, allowing them to perceive aspects of rainbows that remain invisible to us. This suggests that the rainbows we see and admire are just a fraction of the full display. Nature provides a humbling reminder that our perception of the world, while rich and detailed, is still limited by the capabilities of our sensory systems. The relationship between rainbow colors and human emotion has been studied by psychologists who find that rainbow sightings consistently improve mood and create feelings of hope and wonder. This isn't just cultural conditioning, but seems to be a deep psychological response to these displays of natural beauty, perhaps because rainbows signal the end of storms and the return of clear weather. They've become associated in our minds with positive change and renewal. Double rainbows create their own special magic, with the secondary arc appearing like an echo of the first, but with colors reversed. This reversal happens because light undergoes an additional reflection inside the water, droplets flipping the color sequence, the space between the two rainbows. Alexander's dark band appears darker than the surrounding sky because less light is scattered in that direction, creating a subtle but noticeable contrast that frames both arcs. The intensity of rainbow colors varies with the angle of the sun and the density of water droplets, creating a range of effects from faint pastel arcs barely visible against bright clouds to vivid saturated bands that seem to glow with their own light. This variability means that no two rainbow experiences are identical, each one offering its own particular combination of colors, brightness, and atmospheric conditions. Circular rainbows visible from aircraft reveal the complete geometry of these phenomena, showing how what we see from the ground is just a small section of a perfect circle. This complete view helps us understand that rainbows aren't really arcs at all, but circles that we perceive as arcs, because the ground blocks our view of the lower portion. Seeing a full circular rainbow is like getting a glimpse behind the curtain of nature's light show. The formation of rainbows requires a delicate balance of conditions that must align with precision. The sun must be shining, the air must contain water droplets of the right size, The droplets must be positioned at the correct angle, and the observer must be in the right location to see the result when all these factors come together. The result is one of nature's most spectacular displays, a reminder of how complex processes can create moments of simple beauty. Supernumerary rainbows, those faint additional bands that sometimes appear inside the primary arc, are caused by interference between light waves. This quantum mechanical effect creates alternating bright and dark fringes that appear as delicate colored bands. These ghostly additions to the main rainbow demonstrate how even the most familiar phenomena can reveal new layers of complexity when examined closely. The width of rainbow bands depends on the uniformity of droplet sizes in the atmosphere when droplets are all approximately the same size. The rainbow appears with sharp, well-defined color bands. When droplet sizes vary widely, the colors blend together, creating a softer, more diffuse appearance. This relationship between droplet characteristics and rainbow appearance allows atmospheric scientists to infer information about cloud properties and precipitation processes. Rainbow photography presents unique challenges because cameras don't see polarized light the same way human eyes do what appears as a vivid rainbow. To the naked eye might appear much fainter in photographs, or conversely, a rainbow that seems faint to the eye might photograph with surprising intensity depending on the camera settings and filters used. This difference between human and photographic perception adds another layer to the complexity of these optical phenomena. The electromagnetic spectrum extends far beyond the visible colors we see in rainbows. Ultraviolet and infrared light are also present in sunlight and also get separated by water droplets. But our eyes can't detect these wavelengths. Specialized cameras can reveal these invisible rainbow extensions, showing that the displays we see are just a small portion of the full spectrum separation occurring in the atmosphere. Seasonal changes in atmospheric conditions affect rainbow frequency and characteristics. Spring thunderstorms, with their combination of intense sunlight and scattered showers, create ideal rainbow conditions, while winter precipitation often occurs with overcast skies that hide the sun. These seasonal patterns mean that rainbow sightings aren't randomly distributed throughout the year, but follow predictable patterns related to weather and climate. The study of rainbows connects to fundamental questions about the nature of light and color that have puzzled scientists and philosophers for centuries. What we perceive as color is really our brain's interpretation of different electromagnetic wavelengths. The colors in a rainbow don't exist in the light itself, but are created by the interaction between the light and our visual system. This reminds us that much of what we consider reality is actually a construction of our perceptual apparatus. Atmospheric conditions that create rainbows reveal fascinating details about the invisible world around us. Temperature gradients in the air can bend light rays slightly, altering the shape and position of rainbow arcs, while humidity levels determine how long water droplets remain suspended and how clearly defined the rainbow bands appear. Meteorologists have learned to read these subtle variations, like a language written in colored light, each rainbow telling a story about wind patterns, pressure systems, and the delicate dance of moisture through the atmosphere. The physics of light scattering that creates rainbows also explains why the sky appears blue and why sunsets paint the horizon in warm oranges and reds. Smaller particles in the atmosphere scatter shorter wavelengths like blue more effectively than longer wavelengths like red. This same principle, working in reverse, helps create the pure spectral colors we see separated in rainbow bands, where each wavelength finds its own precise path through the water droplets, creating that familiar sequence of colors that never varies. Water droplets act as millions of tiny laboratories, each one conducting the same elegant experiment with light. The surface tension that gives droplets their nearly spherical shape is crucial to rainbow formation. Irregular shaped droplets would scatter light chaotically, but the natural tendency of water to form perfect spheres creates the precise geometry needed for rainbow colors to emerge cleanly separated. This is why rainbows appear most vivid when atmospheric conditions create droplets of optimal size and shape. The speed of light changes as it passes through different materials, and this change in speed is what causes the bending or refraction that separates white light into its component colors. Red light slows down less than blue light when entering water, creating different bending angles for each color. This differential bending is like nature's own prism, separating the hidden rainbow that travels with every beam of sunlight, waiting for the right conditions to reveal itself. Ancient cultures around the world developed their own explanations for rainbows long before the physics was understood. Yet remarkably, many of these cultural interpretations captured something essential about the phenomenon. The idea of rainbows as bridges or pathways reflects the way these arcs seem to connect different parts of the sky, creating visual links across vast distances. The notion of rainbows as divine messages speaks to their sudden appearance and ephemeral nature, arriving like gifts and disappearing just as mysteriously. The geometry of rainbow formation means that the colors you see depend entirely on your position relative to the sun, and the water droplets move even a short distance, and you're seeing light from completely different droplets following slightly different paths. This personal nature of rainbow viewing means that while we can share the experience of seeing a rainbow, we can never truly see the identical rainbow that someone else is seeing. Each person's rainbow is as unique as their fingerprint. Interference patterns in light waves create some of the most delicate rainbow effects when light waves from different paths through a water droplet meet. They can either reinforce each other, creating brighter regions, or cancel each other out, creating darker bands. This wave nature of light adds layers of complexity to rainbow formation that weren't understood until quantum mechanics revealed how light behaves both as particles and waves simultaneously. The polarization of rainbow light occurs because the reflection and refraction processes inside water droplets affect different orientations of light waves differently. This polarization is why sunglasses can dramatically change your view of a rainbow, sometimes making colors more vivid by reducing glare, and sometimes causing parts of the rainbow to disappear entirely as certain polarized components are filtered out. Rainbow duration depends on how long the atmospheric conditions remain stable for the rainbow geometry to persist. The sun must continue shining, the water droplets must remain in the air at the proper density and size distribution, and the observer must maintain a position where the angles work correctly. When any of these factors change, the rainbow fades or disappears, sometimes gradually as conditions shift, and sometimes instantly as clouds move across the sun. The mathematics describing rainbow formation involve elegant equations that connect the wavelength of light to the angle at which it emerges from water droplets. These mathematical relationships, discovered through centuries of careful observation and experimentation, reveal the deep order underlying what appears to be a simple natural phenomenon. The precision of these mathematical descriptions allows scientists to predict exactly where rainbow colors will appear. Droplet evaporation affects rainbow persistence as water droplets in the air gradually shrink due to evaporation. The optical properties change, causing rainbow colors to shift and fade. This natural process puts a time limit on rainbow visibility, creating the ephemeral quality that makes rainbow sightings feel so precious and fleeting, like glimpses of something too beautiful for the ordinary world to contain for long. The relationship between rainbow brightness and background lighting creates dramatic variations in visibility. A rainbow against a dark storm cloud appears brilliant and vivid, while the same rainbow against a bright white cloud might be barely perceptible. This contrast effect explains why the most memorable rainbows often emerge from dramatic weather conditions where dark skies provide the perfect canvas for nature's light show. Atmospheric turbulence can cause rainbows to shimmer and dance as air currents move water droplets, creating slight changes in the optical paths. These subtle movements give rainbows a living quality, making them appear to breathe and pulse with the rhythm of the atmosphere. This dynamic character adds to their mystique, transforming what could be a static display into something that seems almost alive. The electromagnetic spectrum extends far beyond visible light, and water droplets separate these invisible wavelengths, just as they separate visible colors. Specialized instruments can detect ultraviolet and infrared rainbows, invisible to human eyes, revealing that the displays we see represent only a small fraction of the full spectrum separation occurring in the atmosphere. These invisible rainbows remind us how much of the natural world remains hidden from our direct perception. Temperature variations within rain clouds affect droplet size distribution, creating subtle differences in rainbow appearance. Warmer regions tend to produce larger droplets, while cooler areas create smaller ones. This temperature dependence means that rainbows carry encoded information about the thermal structure of the atmosphere for those who know how to interpret the subtle variations in color intensity and band sharpness. The study of rainbow formation has contributed to advances in meteorology, optics, and atmospheric science. Understanding how light interacts with water droplets helps scientists design better weather radar systems, develop improved optical instruments, and create more accurate climate models. The same principles that create beautiful rainbows also inform practical technologies that benefit society in countless ways. Multiple scattering within dense clouds can create complex rainbow effects where light bounces between many droplets before reaching the observer. These higher order interactions produce faint additional arcs and subtle color variations that add richness to the overall display. These complex scattering processes demonstrate how even well understood phenomena can reveal new layers of detail when examined under different conditions. The curvature of rainbow arcs reflects the spherical geometry of the light scattering process. Each point along the rainbow arc represents light scattered at the same angle from droplets arranged in a circle around the observer. This geometric relationship explains why rainbows maintain their consistent arc shape, regardless of the size or position of the rain cloud, creating them seasonal variations. In sun angle affect rainbow size and position. Summer rainbows, when the sun is high, appear as smaller arcs lower in the sky, while winter rainbows, with the sun at lower angles, create larger arcs that span more of the heavens. This seasonal cycle means that rainbow experiences change throughout the year, offering different perspectives on the same fundamental phenomenon. The discovery that white light contains all colors revolutionized our understanding of both light and color. Before this revelation, scientists believed that prisms and raindrops somehow added color to white light, rather than revealing colors that were already present. This paradigm shift illustrates how studying natural phenomena like rainbows can lead to fundamental advances in scientific understanding. Atmospheric pressure affects the density of air and water vapor, influencing how light travels through the atmosphere and how water droplets form and persist. These pressure effects create subtle variations in rainbow appearance that experienced observers can learn to recognize, connecting rainbow characteristics to broader weather patterns and atmospheric conditions. The relationship between droplet concentration and rainbow intensity follows predictable patterns. Too few droplets and the rainbow appears faint and incomplete. Too many droplets and the colors become washed out by multiple scattering effects. The optimal concentration creates vivid, well-defined color bands that seem to glow with inner light. This Goldilocks zone of droplet density explains why some rainbow sightings are dramatically more impressive than others. Laboratory studies of rainbow formation using controlled water sprays and artificial light sources have revealed the details impossible to observe in natural settings. These experiments allow scientists to isolate individual variables and study their effects on rainbow characteristics, providing insights that enhance our understanding of the natural phenomena we observe in the sky. The speed at which rainbow colors fade varies with wavelength. Red light typically persists longest, while blue and violet fade first as atmospheric conditions change. This differential fading creates subtle shifts in rainbow appearance over time, as the color balance gradually changes from the full spectrum display to increasingly warm-toned arcs before disappearing entirely. Polarimetric analysis of rainbow light reveals information about droplet shape and composition that isn't visible to casual observation. Perfectly spherical droplets create different polarization patterns than slightly flattened or irregular droplets, allowing scientists to infer details about atmospheric conditions and precipitation processes from careful analysis of rainbow light. The quantum mechanical nature of light becomes apparent in some rainbow phenomena, where wave interference creates patterns that classical physics alone cannot fully explain. These quantum effects typically appear as subtle variations in intensity and color distribution that add richness to the overall display while demonstrating the fundamental wave nature of electromagnetic radiation. Wind patterns within rain clouds affect droplet trajectories and size sorting, creating variations in rainbow appearance across the arc. Different parts of the same rainbow may show slightly different characteristics as light interacts with droplets that have experienced different atmospheric conditions. This spatial variation adds complexity to rainbow displays while providing information about atmospheric dynamics. The relationship between observer elevation and rainbow visibility follows geometric principles that become apparent when viewing rainbows from different heights. Aircraft passengers sometimes see complete circular rainbows, while ground observers see only arcs. This elevation effect demonstrates how perspective shapes our perception of natural phenomena, revealing aspects of reality that remain hidden from our usual vantage points. Atmospheric scientists have discovered that rainbow formation serves as a natural barometer for understanding precipitation patterns and cloud dynamics. Each rainbow carries encoded information about the atmospheric conditions that created it, like a colorful signature written across the sky. Meteorologists can read these signatures to infer details about temperature, humidity, wind patterns, and droplet size distribution within rain clouds. This makes rainbows not just beautiful displays, but also valuable scientific instruments for studying weather systems. The relationship between sunlight angle and rainbow geometry creates predictable patterns throughout the day. Morning rainbows appear in the western sky as the sun rises in the east, while evening rainbows grace the eastern horizon as the sun sets in the west. This daily dance of light and position means that rainbow chasers can actually predict where rainbows are most likely to appear based on time of day, weather conditions, and their geographic location. Interference effects between light waves create some of the most delicate rainbow phenomena when light takes multiple paths through a water droplet. The waves can interfere with each other, creating alternating bands of brightness and darkness. These interference patterns appear as supernumerary bows, those ghostly additional arcs that sometimes flicker inside the main rainbow, like echoes of color that remind us light behaves in ways that still seem magical even when we understand the physics. The persistence of rainbows depends on atmospheric stability conditions that remain constant. Allow rainbows to linger while changing weather patterns cause them to shift, fade, or disappear. The longest lasting rainbows occur when weather systems move slowly and atmospheric conditions remain uniform across large areas, creating stable platforms for these optical displays to maintain their geometry and intensity. Droplet size evolution affects rainbow characteristics over time as water droplets in the atmosphere gradually evaporate or coalesce. Their optical properties change, causing subtle shifts in rainbow appearance. What begins as a vivid arc with sharp color boundaries might slowly transform into a softer, more diffuse display as the droplets that create it undergo natural changes. This temporal evolution gives rainbows a living quality that makes each viewing experience unique. The scattering of different wavelengths by atmospheric particles influences rainbow visibility and color balance. Blue light scatters more readily than red light, which is why blue skies fade to warm colors. At sunset, this same scattering principle affects rainbow formation with atmospheric conditions, determining which colors reach our eyes, most effectively creating variations in the apparent intensity and hue of different rainbow bands. Laboratory experiments with controlled water droplets have revealed how slight changes in droplet shape affect rainbow formation. Perfectly spherical droplets create the most vivid rainbows, while slightly flattened or irregular droplets produce softer, less defined color bands. This relationship between droplet geometry and optical performance explains why natural rainbows vary so dramatically in clarity and intensity depending on atmospheric conditions. The electromagnetic spectrum extends far beyond visible light, and the same refraction processes that create visible rainbows also separate invisible ultraviolet and infrared radiation. These invisible rainbow extensions contain information about atmospheric composition and solar radiation that remains hidden from our eyes but can be detected by specialized instruments, revealing the full scope of the spectral separation occurring in every rainbow display. Multiple reflection paths within water droplets create complex optical phenomena where light can take several different routes before emerging as visible rainbow colors. These higher order reflections produce secondary and tertiary rainbows that are much fainter than the primary arc, but add richness and complexity to the overall display when atmospheric conditions are just right to make them visible. The polarization characteristics of rainbow light vary with position along the arc, creating patterns that can be detected by polarizing filters or specialized instruments. This polarization information encodes details about the optical paths light has taken through the water droplets, providing another layer of information about atmospheric conditions. For scientists who know how to interpret these subtle signals, atmospheric turbulence creates dynamic effects in rainbow displays as air currents move water droplets around, creating slight variations in the optical geometry. This movement can cause rainbows to shimmer, dance, or pulse with subtle changes in intensity and color distribution, adding a living quality to what might otherwise appear as static arcs of light. The relationship between background illumination and rainbow visibility demonstrates how contrast affects our perception of optical phenomena. Rainbows appear most vivid against dark storm clouds, where the contrast enhances color saturation, while appearing much fainter against bright white clouds, where the lack of contrast makes colors difficult to distinguish. This contrast dependence explains why dramatic weather often produces the most memorable rainbow sightings. Temperature gradients in the atmosphere can create subtle bending effects that alter rainbow geometry. Warm and cool air masses have different refractive properties, causing light rays to follow slightly curved paths rather than straight lines. These thermal effects can cause rainbows to appear higher or lower than expected and can create unusual distortions in the arc shape. The formation of ice crystal rainbows occurs when sunlight interacts with hexagonal ice crystals rather than water droplets. These phenomena produce displays with different geometric characteristics than water droplet rainbows, including sundogs, parhelia, and circumhorizontal arcs that follow the crystalline structure of ice rather than the spherical geometry of liquid water. Droplet concentration gradients within rain clouds create variations in rainbow intensity along the arc. Different parts of the same rainbow may appear brighter or dimmer, depending on the local density of water droplets in the corresponding regions of the rain cloud. This spatial variation adds complexity to rainbow displays, while providing information about the internal structure of precipitation systems. The quantum mechanical properties of light become apparent in rainbow formation through wave interference effects that create fine structure in the color bands. These quantum phenomena typically appear as subtle variations in intensity that add richness to the overall display while demonstrating the fundamental wave nature of electromagnetic radiation. Atmospheric chemistry affects rainbow formation through the interaction of sunlight with various gases and particles in the air. Different atmospheric compositions can alter the scattering and absorption of specific wavelengths, creating subtle variations in rainbow color balance and intensity. Those chemical effects are usually minor, but can be detected in careful observations of rainbow spectra. The speed of rainbow formation depends on how quickly atmospheric conditions align to create the necessary optical geometry when conditions change rapidly. Rainbows can appear and disappear in seconds, while gradual atmospheric changes allow rainbows to form slowly and persist for extended periods. This temporal variability adds to the ephemeral quality that makes rainbow sightings feel so special. Wind shear effects within rain clouds can create differential motion of water droplets at different altitudes, causing variations in rainbow characteristics with height. Different parts of the same rainbow arc may show slightly different properties as they originate from droplets, experiencing different wind conditions. This vertical variation demonstrates how atmospheric dynamics influence optical phenomena. The mathematical description of rainbow formation involves elegant equations that connect physical properties like wavelength and refractive index to observable characteristics like color position and intensity. These mathematical relationships allow scientists to predict rainbow properties with remarkable precision while revealing the deep geometric principles underlying these natural displays. Seasonal changes in atmospheric conditions create patterns in rainbow frequency and characteristics. Spring and summer thunderstorms provide ideal conditions for rainbow formation, with their combination of intense sunlight and scattered precipitation, while winter conditions often lack the proper balance of sun and rain needed for vivid rainbow displays. The discovery that rainbows follow universal physical laws, regardless of geographic location or cultural context, demonstrates how natural phenomena transcend human boundaries. The same optical principles that create rainbows over tropical islands also govern their formation over Arctic tundra, connecting diverse environments through shared physical processes. Atmospheric pressure variations affect the density and refractive properties of air, creating subtle influences on rainbow formation. High pressure systems, with their associated clear skies, often provide excellent conditions for rainbow visibility, while low pressure systems may create the precipitation needed but lack the clear skies necessary for sunlight to create the displays. The relationship between droplet fall velocity and rainbow stability reveals how dynamic processes affect optical phenomena. Faster falling droplets create less stable rainbow conditions, while slowly settling droplets allow rainbows to persist longer. This velocity dependence explains why light mist often produces longer lasting rainbows than heavy downpours. Spectroscopic analysis of rainbow light can reveal information about atmospheric composition and solar radiation characteristics by carefully measuring the intensity of different wavelengths. In rainbow displays, scientists can infer details about atmospheric particles, aerosols, and even trace gases that affect how sunlight travels through the atmosphere. The formation of reflection rainbows over bodies of water creates complex optical displays where primary rainbows appear to extend both above and below the horizon. These reflection effects occur when sunlight reflects off water surfaces before interacting with atmospheric water droplets, creating the illusion of complete rainbow circles extending from sky to water. Multiple scattering events within dense water, droplet clouds, can create higher order rainbow phenomena, where light undergoes several reflections and refractions before reaching the observer. These complex optical paths produce faint additional arcs and subtle color variations that add depth and richness to the overall rainbow display. The relationship between human color perception and rainbow observation reveals how our visual system interprets electromagnetic radiation. The colors we see in rainbows result from our brain's processing of different wavelengths rather than being inherent properties of the light itself. This perceptual aspect connects rainbow science to neuroscience and psychology. Atmospheric lensing effects can focus or defocus rainbow light, creating variations in apparent brightness and sharpness along the arc. These lensing phenomena occur when temperature or humidity gradients in the atmosphere act like weak optical elements, altering the paths of light rays and creating subtle modifications to rainbow geometry. The study of rainbow formation has contributed to advances in optical engineering, meteorology, and atmospheric science. Understanding how light interacts with water droplets has informed the development of technologies ranging from weather radar systems to optical communication devices, demonstrating how basic research into natural phenomena leads to practical applications. Particle size distribution within precipitation systems determines the width and clarity of rainbow color bands. Uniform droplet sizes create sharp, well defined rainbows, while variable droplet sizes produce broader, softer color transitions. This relationship between particle characteristics and optical properties allows meteorologists to infer precipitation details from rainbow observations. The electromagnetic signature of rainbow formation extends across multiple wavelengths, from ultraviolet through visible light to infrared radiation. Each wavelength range carries different information about atmospheric conditions and solar radiation, creating a rich, multispectral phenomenon that extends far beyond what human eyes can perceive. Thermal effects in the atmosphere create convection patterns that influence water, droplet distribution, and movement, affecting rainbow formation and persistence. Rising warm air can lift droplets to optimal altitudes for rainbow formation, while descending cool air can disperse droplet clouds and cause rainbows to fade. The polarimetric properties of rainbow light encode information about droplet shape, orientation, and internal structure that remains invisible to casual observation. Specialized instruments can analyze these polarization characteristics to infer details about atmospheric physics and precipitation processes. Atmospheric turbulence creates dynamic variations in rainbow displays as air currents constantly move and redistribute water droplets, causing subtle changes in optical paths. This atmospheric motion gives rainbows their living, breathing quality, making them appear to pulse and shimmer with the rhythm of the air itself. The geometric relationship between sun-angle droplet position and observer location creates the precise angular requirements for rainbow visibility. These geometric constraints explain why rainbows appear at specific positions in the sky, and why moving even short distances can dramatically change the rainbow viewing experience. Chemical composition of atmospheric water affects rainbow formation through subtle changes in refractive properties. Pure water droplets create different optical effects than droplets containing dissolved salts, minerals, or other substances. These compositional effects are usually minor, but can be detected in careful spectroscopic analysis of rainbow light. The discovery that rainbow colors represent the fundamental wavelengths of visible light revolutionized our understanding of both optics and the nature of electromagnetic radiation. This revelation connected rainbow phenomena to broader principles of physics, including quantum mechanics and electromagnetic theory, atmospheric dynamics, create complex patterns of water droplet movement that influence rainbow stability and appearance. Wind patterns, pressure gradients, and convection currents all affect how droplets move through the atmosphere, determining how long rainbow conditions persist and how the displays evolve over time. The relationship between droplet surface tension and rainbow formation demonstrates how molecular forces influence large scale optical phenomena. The spherical shape that surface tension gives to water droplets is crucial for creating the precise geometry needed for rainbow colors to separate cleanly and appear as distinct bands. Laboratory studies using artificial water droplets and controlled lighting conditions have revealed details about rainbow formation that are impossible to observe in natural settings. These experiments allow scientists to isolate individual variables and study their effects systematically, providing insights that enhance understanding of natural rainbow phenomena. The temporal evolution of rainbow displays reflects changing atmospheric conditions. As weather systems move and evolve, what begins as a faint arc might strengthen into a vivid display before gradually fading as conditions change. This temporal variability connects rainbow observations to broader meteorological patterns and atmospheric dynamics. Quantum interference effects in rainbow formation create fine structure in the color bands that adds richness and complexity to the overall display. These quantum phenomena demonstrate how fundamental physics principles manifest in everyday natural phenomena, creating beauty through the same processes that governs atomic and molecular behavior. The relationship between atmospheric moisture content and rainbow formation involves complex interactions between humidity, precipitation, and solar radiation. Optimal rainbow conditions require a delicate balance of these factors, with too little moisture preventing droplet formation and too much moisture blocking sunlight. Wind patterns at different altitudes create vertical variations in droplet characteristics, affecting rainbow appearance with height. Different layers of the atmosphere may contain droplets with different sizes, velocities, and concentrations, creating subtle variations along the rainbow arc that encode information about atmospheric structure. The mathematical elegance of rainbow geometry reveals deep connections between physics, mathematics, and natural beauty. The precise angles, wavelength relationships, and geometric constraints that govern rainbow formation demonstrate how mathematical principles underlie even the most ephemeral and seemingly magical natural phenomena. Atmospheric particle interactions affect rainbow formation through scattering, absorption, and emission processes that modify sunlight before it reaches water. Droplets, dust, pollen, aerosols, and other particles can alter the spectral composition of incident light, creating subtle variations in resulting rainbow characteristics. The persistence of cultural fascination with rainbows across all human societies suggests something profound about how these displays connect with human psychology and aesthetic sensibility. Perhaps the combination of beauty, ephemeral nature, and scientific complexity makes rainbows uniquely appealing to both emotional and intellectual responses. Seasonal atmospheric chemistry changes affect rainbow formation through variations in air composition, humidity, and temperature patterns. Spring and summer conditions often provide optimal combinations of factors for vivid rainbow displays, while winter conditions may lack the proper balance of sunlight and atmospheric moisture. The discovery that rainbow formation follows predictable physical laws while maintaining an element of unpredictability in timing and location perfectly captures the tension between scientific understanding and natural wonder. We can explain how rainbows form, but we cannot always predict when we will be fortunate enough to witness one atmospheric optics research using rainbow phenomena has advanced our understanding of light, scattering electromagnetic radiation, and meteorological processes. This research connects basic physics principles to practical applications in weather forecasting, climate science, and optical technology development. The relationship between rainbow observation and human emotion demonstrates how natural phenomena can trigger deep psychological responses that transcend cultural and linguistic boundaries. The universal appeal of rainbows suggests fundamental connections between natural beauty, human perception, and aesthetic appreciation. Droplet evaporation. Rates affect rainbow duration and evolution. As atmospheric water gradually returns to vapor form, changing the optical properties that create rainbow displays this natural time limit on rainbow persistence contributes to their precious ephemeral quality that makes each sighting feel like a gift. The electromagnetic spectrum analysis of rainbow light reveals information about solar radiation, atmospheric composition, and optical processes that extends far beyond the visible colors. We observe these invisible aspects of rainbow formation, connect the phenomena to broader questions about electromagnetic radiation and atmospheric physics. Atmospheric pressure gradients create subtle lensing effects that can focus or defocus rainbow light, altering apparent brightness and clarity along the arc. These pressure effects demonstrate how dynamic atmospheric conditions influence optical phenomena in ways that are often too subtle to notice without careful observation. The quantum mechanical description of light behavior in rainbow formation reveals how fundamental physics principles manifest in everyday natural phenomena, connecting the microscopic world of photons and electromagnetic waves to the macroscopic beauty of rainbow displays. The study of rainbow formation connects to fundamental questions about perception and reality that have fascinated philosophers and scientists for centuries. What we experience as color exists not in the electromagnetic radiation itself, but in the complex interaction between light wavelengths and our visual system. The rainbow colors we see are interpretations created by our brains, translations of physical wavelengths into the rich spectrum of hues that paint these celestial arcs. This means that in a very real sense, rainbows exist in the space between the physical world and human consciousness, neither purely objective nor entirely subjective, but something beautifully in between. Atmospheric scientists have discovered that rainbow intensity follows predictable patterns related to droplet density and size distribution when conditions align perfectly with droplets of optimal size, suspended at just the right concentration in the air. The result is those breathtaking displays that seem to glow with inner light, as if nature has turned up the saturation on reality itself. But when droplet characteristics vary widely, or concentrations are too sparse or too dense, the colors become muted and indistinct, reminding us that even the most spectacular natural phenomena depend on delicate balances of countless invisible factors. The speed of light changes as it travels through different materials, and this fundamental property drives the entire rainbow formation process when sunlight encounters the boundary between air and water. It must slow down, and this deceleration causes the light ray to bend or refract, but different colors slow down by different amounts, creating the separation that transforms white light into the spectrum of colors. We see this elegant physics plays out millions of times simultaneously, as countless droplets each act as tiny laboratories conducting the same experiment with light. Temperature variations within rain clouds create complex patterns of droplet formation and movement that influence rainbow characteristics. Warmer regions tend to produce larger droplets that create different optical effects than the smaller droplets formed in cooler areas. This temperature dependence means that rainbows carry encoded information about the thermal structure of the atmosphere, visible to those who understand how to read the subtle variations in color, intensity, brightness, and band definition. The relationship between atmospheric humidity and rainbow formation involves intricate feedback loops where moisture content affects both droplet formation and the clarity of the air through which light must travel. Too little humidity prevents adequate droplet formation, while excessive moisture can create haze that diffuses and scatters light before it reaches the water. Droplets, the sweet spot for optimal rainbow formation, requires atmospheric conditions that are moist enough to sustain droplets, but clear enough to allow crisp sunlight to illuminate them. Interference patterns in light waves create some of the most delicate and ephemeral rainbow effects when light waves traveling different paths through water. Droplets meet, they can either reinforce each other, creating brighter regions, or cancel each other out, creating darker bands. These wave interference phenomena produce the ghostly supernumerary arcs that sometimes appear as faint colored fringes inside the main rainbow, like whispered echoes of the primary display. The electromagnetic spectrum extends far beyond the narrow band of wavelengths our eyes can detect, and water droplets separate these invisible portions of sunlight just as efficiently as they separate visible colors. Ultraviolet and infrared rainbows exist alongside the displays. We can see carrying information about solar radiation and atmospheric conditions that remains hidden from our direct perception. These invisible extensions remind us that what we observe represents only a small fraction of the full electromagnetic symphony playing out in every rainbow. Polarization effects in rainbow light create patterns that vary with position along the arc as light reflects and refracts through water droplets. It becomes partially polarized, meaning the electromagnetic waves oscillate in preferred directions. This polarization encodes information about the optical paths light has taken and can be detected using polarizing filters, which can dramatically enhance or diminish rainbow visibility depending on their orientation. Atmospheric turbulence adds a dynamic quality to rainbow displays, as air currents constantly move water droplets, creating subtle shifts in the optical geometry. This movement can cause rainbows to shimmer, pulse, or dance with variations in intensity and color distribution. The living, breathing quality. This gives to rainbow displays connects these optical phenomena to the broader rhythms of atmospheric motion and weather patterns. The curvature of rainbow arcs reflects the spherical geometry underlying the light scattering process. Each point along a rainbow represents light scattered at precisely the same angle from droplets arranged in a circular pattern around the observer. This geometric relationship explains why rainbows maintain their consistent arc shape, regardless of the size, position, or characteristics of the rain cloud that creates them. Seasonal variations in sun angle create predictable changes in rainbow size and position throughout the year. Summer rainbows, when the sun rides high, appear as smaller arcs positioned lower in the sky, while winter displays with the sun at lower angles create larger arcs that can span impressive portions of the heavens. This seasonal cycle offers different perspectives on the same fundamental phenomenon, connecting rainbow observations to the astronomical rhythms that govern our planet. The discovery that white light contains all spectral colors revolutionized scientific understanding of both light and vision. Before this breakthrough, scientists believed that prisms and water droplets somehow added color to colorless light rather than revealing the hidden spectrum that travels with every beam of sunlight. This paradigm shift illustrates how studying natural phenomena can lead to fundamental advances in human knowledge. Droplet size evolution affects rainbow persistence, as water droplets suspended in the atmosphere gradually change through evaporation, condensation, or collision with other droplets. These changes alter the optical properties, creating subtle shifts in rainbow appearance over time. What begins as a sharp, vivid display might slowly transform into a softer, more diffuse arc as the droplets that create it undergo natural evolutionary processes. The relationship between observer elevation and rainbow visibility follows geometric principles that become apparent when viewing these displays from different heights. Mountain climbers and aircraft passengers sometimes witness complete circular rainbows, while ground level observers see only arcs. This elevation effect demonstrates how perspective shapes our perception, revealing aspects of natural phenomena that remain hidden from our usual vantage points. Atmospheric chemistry influences rainbow formation through the interaction of sunlight with various gases, particles, and aerosols suspended in the air. Different atmospheric compositions can alter the scattering, absorption, and transmission of specific wavelengths, creating subtle variations in rainbow color balance and intensity. These chemical effects connect rainbow observations to broader questions about air quality, atmospheric composition, and environmental monitoring. The mathematical description of rainbow formation involves elegant equations that relate physical properties like wavelength, refractive index, and scattering angle to observable characteristics such as color position and brightness. These mathematical relationships allow scientists to predict rainbow properties with remarkable precision while revealing the deep geometric principles that govern these natural light shows. Laboratory experiments using controlled water sprays and artificial illumination have revealed aspects of rainbow formation impossible to study in natural settings. These controlled investigations allow researchers to isolate individual variables and examine their effects systematically, providing insights that enhance understanding of the complex atmospheric processes that create natural rainbow displays. The quantum mechanical nature of light becomes apparent in certain rainbow phenomena where wave properties create effects that classical physics alone cannot fully explain. These quantum aspects typically manifest as subtle variations in intensity and color distribution that add richness to the overall display while demonstrating the fundamental wave nature of electromagnetic radiation. Wind patterns within precipitation systems affect droplet trajectories and sorting, creating spatial variations in rainbow characteristics. Different parts of the same rainbow may exhibit slightly different properties as they originate from droplets that have experienced different atmospheric conditions. This spatial heterogeneity adds complexity to rainbow displays while encoding information about atmospheric dynamics. The relationship between background lighting and rainbow contrast demonstrates how environmental conditions affect the visibility of optical phenomena. Rainbows appear most vivid against dark storm clouds, where high contrast enhances color saturation, while seeming much fainter against bright backgrounds, where poor contrast makes colors difficult to distinguish. This contrast dependence explains why dramatic weather often produces the most memorable rainbow sightings. Atmospheric pressure variations create subtle but measurable effects on rainbow formation through changes in air density and refractive properties. High pressure systems often provide excellent visibility conditions for rainbow observation, while low pressure systems may generate the precipitation needed but lack the atmospheric clarity required for optimal displays. The formation of multiple rainbow arcs occurs when light undergoes additional reflections within water droplets, creating secondary and even tertiary displays that appear at different angular positions with reversed color sequences. These higher order rainbows are much fainter than the primary arc, but add depth and complexity to the overall phenomenon when atmospheric conditions align perfectly for their visibility. Spectroscopic analysis of rainbow light can reveal detailed information about atmospheric composition, solar radiation, characteristics, and optical processes by carefully measuring the intensity of different wavelengths. Scientists can infer properties of atmospheric particles, aerosols, and trace gases that influence how sunlight travels through the atmosphere. The persistence of rainbow displays depends on atmospheric stability, with steady conditions allowing these optical phenomena to maintain their geometry and intensity, while changing weather patterns cause them to shift, fade, or disappear. The longest lasting rainbows occur when meteorological systems move slowly and atmospheric properties remain uniform across large geographical areas. Droplet concentration gradients within rain systems create variations in rainbow brightness along the arc, as different regions contain different densities of water, droplets leading to corresponding variations in light scattering intensity. This spatial variation provides information about the internal structure and dynamics of precipitation systems while adding visual complexity to rainbow displays. The electromagnetic signature of rainbows extends across multiple wavelength ranges, from ultraviolet through visible light to infrared radiation. Each spectral region carries different information about atmospheric conditions and solar characteristics, creating a rich, multispectral phenomenon that far exceeds what human vision can directly perceive. Thermal gradients in the atmosphere can create refractive effects that subtly alter rainbow geometry, as warm and cool air masses have different optical properties, causing light rays to follow slightly curved paths rather than straight lines. These thermal influences can cause rainbows to appear at unexpected positions or with unusual distortions in their arc shapes. The study of rainbow formation has contributed to advances in meteorology, atmospheric science, and optical engineering, with insights from rainbow research informing the development of weather monitoring systems, optical instruments, and atmospheric modeling techniques. This demonstrates how basic research into natural phenomena often leads to practical technological applications. Interference effects between light waves create fine structure in rainbow displays that adds subtle richness and complexity to the color bands. These interference patterns result from the wave nature of light and typically appear as delicate variations in intensity that enhance the overall visual appeal while revealing fundamental properties of electromagnetic radiation. The relationship between human color perception and rainbow observation connects optical physics to neuroscience and psychology, as the colors we see result from our brain's interpretation of electromagnetic wavelengths rather than being inherent properties of the light itself. This perceptual aspect adds another layer of complexity to rainbow science, bridging physical and biological sciences. Atmospheric lensing effects can focus or defocus rainbow light, creating variations in apparent sharpness and brightness along the arc. These optical phenomena occur when temperature or humidity gradients act like weak lenses, altering light ray paths and creating subtle modifications to rainbow geometry that encode information about atmospheric structure. The formation of ice crystal displays follows different optical principles than water droplet rainbows, with hexagonal ice crystals creating phenomena like sundogs, halos, and circumhorizontal arcs that exhibit their own geometric patterns and color characteristics. These crystalline optical effects demonstrate how different forms of atmospheric water create diverse types of light displays. Particle size distribution within precipitation determines the clarity and definition of rainbow color bands, with uniform droplet sizes creating sharp, well-defined displays, while variable sizes produce broader, softer color transitions. This relationship allows meteorologists to infer precipitation characteristics from careful observation of rainbow properties. The discovery that rainbow phenomena follow universal physical laws, regardless of geographic location or cultural context, demonstrates how natural processes transcend human boundaries, connecting diverse environments through shared optical and atmospheric principles that operate consistently across the planet. Atmospheric dynamics create complex patterns of droplet movement that influence rainbow stability and evolution. As wind systems, pressure gradients, and convection currents affect how water droplets move through the atmosphere, determining how long optimal conditions persist and how displays change over time. The relationship between droplet surface tension and optical properties demonstrates how molecular forces influence large-scale phenomena. As the spherical shape that surface tension gives to water droplets is crucial for creating the precise geometry needed for clean color separation and distinct spectral bands. Chemical composition variations in atmospheric water can subtly affect rainbow formation through change in refractive properties, as dissolved substances alter how light behaves when passing through droplets. Though these effects are typically minor, they can be detected through careful spectroscopic analysis. The temporal evolution of rainbow displays reflects the dynamic nature of atmospheric systems, as changing weather conditions cause these optical phenomena to strengthen, weaken, shift position, or disappear entirely. This temporal variability connects rainbow observations to broader meteorological patterns and atmospheric physics. Quantum interference phenomena in rainbow formation demonstrate how fundamental physics principles manifest in everyday natural displays, creating subtle effects that add depth and richness to the overall spectacle while illustrating the wave nature of electromagnetic radiation at scales. We can directly observe the mathematical elegance underlying rainbow geometry, reveals deep connections between physics, mathematics, and natural beauty, as the precise angular relationships, wavelength dependencies, and geometric constraints that govern these displays demonstrate how mathematical principles create some of nature's most stunning visual phenomena. Atmospheric moisture dynamics involve complex interactions between evaporation, condensation, and precipitation that determine when and where conditions become optimal for rainbow formation, requiring delicate balances of humidity, solar radiation, and atmospheric clarity that align only under specific meteorological circumstances. The relationship between rainbow observation and emotional response appears to be universal across human cultures, suggesting fundamental connections between natural beauty, human psychology, and aesthetic appreciation that transcend individual differences in background experience or cultural conditioning. Wind shear effects at different atmospheric levels create variations in droplet characteristics with altitude as different air layers move at different speeds, affecting droplet formation, distribution, and persistence in ways that influence rainbow appearance and create vertical variations along the display arc. The electromagnetic analysis of rainbow spectra provides insights into solar radiation, atmospheric transmission, and optical processes that extend far beyond the visible phenomenon, connecting these beautiful displays to broader questions about electromagnetic radiation, atmospheric physics, and solar science. Atmospheric pressure gradients influence rainbow formation through effects on air density, refractive properties, and atmospheric clarity, with different pressure conditions creating subtle variations in how light travels through the atmosphere and interacts with suspended water droplets. The discovery that rainbow colors represent fundamental wavelengths of electromagnetic radiation connected these natural phenomena to broader principles of physics, including quantum mechanics, atomic structure, and the nature of light itself, revolutionizing scientific understanding of electromagnetic radiation. Seasonal changes in atmospheric composition affect rainbow formation through variations in humidity temperature, aerosol content, and atmospheric chemistry that influence both droplet formation and light transmission, creating predictable patterns in rainbow frequency and characteristics throughout the year. The persistence of scientific interest in rainbow phenomena demonstrates how even well understood natural processes continue to reveal new layers of complexity and beauty as advancing technology and theoretical understanding provide new tools for investigation and deeper insights into atmospheric optics. Laboratory investigations using artificial droplets and controlled illumination have revealed detailed mechanisms of rainbow formation that remain invisible in natural settings, allowing scientists to study individual aspects of the phenomenons systematically and develop more complete theoretical models of atmospheric optical processes. The relationship between atmospheric turbulence and rainbow dynamics shows how air motion creates the living, breathing quality that makes these displays appear to pulse and shimmer with the rhythm of atmospheric circulation patterns, connecting optical phenomena to meteorological processes and fluid dynamics. Droplet fall velocities affect rainbow stability, as faster falling precipitation creates less stable optical conditions, while slowly settling mist allows rainbow geometry to persist longer. This velocity dependence explains why light drizzle often produces longer lasting displays than heavy downpours. The geometric relationship between sun position, droplet location, and observer viewpoint creates the precise angular requirements for rainbow visibility, explaining why these phenomena appear at specific sky positions and why small changes in viewing location can dramatically alter the rainbow experience. Atmospheric chemistry research using rainbow spectroscopy has advanced understanding of air composition, trace gas concentrations, and aerosol properties. By analyzing how different atmospheric constituents affect the transmission and scattering of rainbow light, providing valuable environmental monitoring capabilities. The quantum mechanical description of light behavior in rainbow formation connects macroscopic optical phenomena to microscopic quantum processes, demonstrating how fundamental physics principles operating at atomic scales create the large-scale beauty we observe in natural rainbow displays. Multiple scattering processes within dense droplet clouds create complex optical effects where light undergoes several interactions before reaching observers, producing subtle additional features and color variations that add depth and richness to rainbow displays under optimal atmospheric conditions. The relationship between human vision and rainbow perception reveals how our sensory systems interpret electromagnetic information with individual variations in color, sensitivity, and processing affecting how different people experience the same optical phenomenon, connecting rainbow science to vision research and perceptual psychology. Atmospheric particle interactions influence rainbow formation through scattering absorption and fluorescence processes that modify incident sunlight before it reaches water droplets, creating subtle variations in spectral composition that affect resulting rainbow characteristics and provide information about atmospheric composition. The discovery that rainbow formation involves both geometric optics and wave interference demonstrates how different aspects of light behavior contribute to these complex phenomena, requiring sophisticated theoretical frameworks that incorporate multiple physics principles to fully explain observed characteristics. Thermal convection patterns in the atmosphere create vertical air motions that affect droplet distribution and movement, influencing rainbow formation, persistence, and evolution as rising warm air and descending cool air transport water droplets through different atmospheric layers with varying optical properties. The electromagnetic spectrum extension of rainbow phenomena into invisible wavelength ranges reveals the full scope of spectral separation occurring in atmospheric water droplets, providing information about solar radiation and atmospheric processes that remains hidden from direct human observation but can be detected instrumentally. Atmospheric optics research using rainbow phenomena has contributed to advances in weather forecasting, climate modeling, and atmospheric monitoring by improving understanding of how electromagnetic radiation interacts with atmospheric water in its various forms, from droplets to ice crystals. The relationship between background contrast and rainbow visibility demonstrates how environmental lighting conditions affect perception of optical phenomena, with dramatic storm clouds providing optimal contrast for vivid rainbow observation, while bright uniform backgrounds can render the same optical display nearly invisible. Particle size evolution in atmospheric water droplets creates temporal changes in rainbow characteristics as evaporation, condensation, and collision processes gradually alter droplet properties, causing rainbow displays to evolve, shift, and eventually fade as atmospheric conditions change. The mathematical relationships governing rainbow formation reveal elegant connections between wavelength angle and refractive index that allow precise prediction of rainbow properties while demonstrating the geometric principles underlying these natural optical phenomena. Atmospheric stability conditions determine rainbow duration with steady meteorological patterns, allowing extended displays, while changing weather systems cause rapid appearance and disappearance of optimal viewing conditions. Connecting rainbow observations to broader atmospheric dynamics and weather forecasting, the polarimetric analysis of rainbow light provides detailed information about droplet shape orientation and internal structure that remains invisible to casual observation but can be detected using specialized instruments, revealing subtle aspects of atmospheric physics and precipitation processes. Quantum interference effects in rainbow formation create fine spectral structure that adds richness to color bands while demonstrating wave properties of electromagnetic radiation at scales directly observable in natural phenomena, connecting quantum physics to everyday optical experiences. The relationship between atmospheric moisture content and rainbow formation involves complex feedback mechanisms where humidity affects both droplet generation and atmospheric transparency, requiring optimal balances for vivid rainbow displays that connect meteorology, hydrology, and atmospheric optics. Wind pattern analysis using rainbow characteristics provides insights into atmospheric circulation and turbulence. As air motion affects droplet distribution and movement in ways that influence optical properties and create spatial variations in rainbow appearance along the display arc. The electromagnetic signature analysis of rainbow spectra reveals information about solar radiation, atmospheric transmission, and optical processes that extends far beyond visible wavelengths, connecting these beautiful phenomena to broader questions about electromagnetic radiation and atmospheric science. Seasonal atmospheric dynamics create predictable patterns in rainbow occurrence and characteristics as changing weather patterns, solar angles, and atmospheric composition influence the frequency and quality of rainbow displays throughout the annual cycle. The study of rainbow formation demonstrates how complex natural phenomena result from the interaction of multiple physical processes, including geometric optics, wave interference, electromagnetic radiation, and atmospheric dynamics, working together to create displays of extraordinary beauty and scientific interest. The cultural impact of rainbows extends far beyond their scientific explanation, weaving through human consciousness in ways that connect us across time and geography. Every civilization that has looked up at the sky has found meaning in these arcs of light, creating stories, myths, and symbols that speak to something universal in the human experience. Perhaps it is the way rainbows appear suddenly, like gifts from the heavens, or their ephemeral nature reminding us that beauty is precious, precisely because it cannot be grasped or held. Modern technology has allowed us to study rainbows with unprecedented precision, using high speed cameras to capture droplet formation spectrometers, to analyze wavelength distribution, and computer models to predict atmospheric conditions. Yet all this scientific capability somehow enhances rather than diminishes the wonder we feel when we encounter these displays. It is as if understanding the mechanics of poetry makes the verses more beautiful, not less. The relationship between rainbows and human emotion appears to be hardwired into our psychology, with studies showing that rainbow sightings consistently improve mood and create feelings of hope and renewal. This may be because rainbows signal the end of storms and the return of clear weather, connecting them in our minds with positive change and the promise that difficult times will pass, leaving beauty in their wake. Atmospheric scientists continue to discover new aspects of rainbow formation that reveal the incredible complexity hidden within these seemingly simple phenomena. Each investigation uncovers additional layers of interaction between light water and air, demonstrating how even the most familiar natural processes contain depths of intricacy that reward careful study and patient observation. The mathematics of rainbow formation connects to broader principles of wave physics and electromagnetic theory, showing how these beautiful displays serve as natural laboratories for studying fundamental properties of light and matter. The elegant equations that describe rainbow geometry reveal deep relationships between wavelength angle and refractive index that govern how electromagnetic radiation behaves throughout the universe. Droplet dynamics in the atmosphere create constantly changing conditions that make each rainbow viewing experience unique, as water, particles move, evaporate, and interact with air currents. The optical properties shift and evolve, causing rainbow displays to strengthen, weaken, shift position, or fade entirely. This dynamic quality ensures that no two rainbow sightings are ever exactly the same. The electromagnetic spectrum reveals that rainbows extend far beyond visible light, with ultraviolet and infrared components carrying information about atmospheric conditions and solar radiation that remains hidden from our eyes, but can be detected by specialized instruments. These invisible extensions remind us that what we observe represents only a small portion of the full spectral symphony occurring in every rainbow display. Atmospheric turbulence adds a living quality to rainbow displays, as air currents create subtle movements in water droplets, causing the arcs to shimmer and pulse with variations in intensity and color distribution. This dynamic character transforms what could be static optical phenomena into something that seems almost alive, breathing with the rhythm of the atmosphere itself. The precision required for rainbow formation demonstrates how delicate natural balances create extraordinary beauty. The sun must shine at the right angle, water droplets must be suspended at optimal concentrations, atmospheric conditions must remain stable, and observers must be positioned where geometry allows the display to be visible when all these factors align. The result is one of nature's most spectacular light shows. Seasonal variations in rainbow characteristics reflect changing atmospheric conditions throughout the year, with spring and summer thunderstorms providing ideal combinations of intense sunlight and scattered precipitation, while winter conditions often lack the proper balance needed for vivid displays. This seasonal rhythm connects rainbow observations to broader patterns of weather and climate. The study of rainbow formation has practical applications that extend far beyond satisfying curiosity. Understanding how light interacts with atmospheric water helps meteorologists improve weather. Forecasting engineers design better optical systems, and environmental scientists monitor air quality and atmospheric composition. These practical benefits demonstrate how basic research into natural beauty often leads to technological advances. Interference patterns in rainbow light create some of the most delicate optical effects where light waves interact to produce alternating bands of brightness and darkness. These wave phenomena add subtle complexity to rainbow displays while demonstrating fundamental properties of electromagnetic radiation that connect these natural phenomena to quantum physics and wave mechanics. The relationship between observer position and rainbow appearance means that every person sees a unique display created by light from different droplets following different paths. This personal quality of rainbow viewing creates an intimate connection between viewer and phenomenon, as if nature has painted each arc specifically for individual eyes and hearts. Atmospheric chemistry influences rainbow formation through interactions between sunlight and various gases, particles, and aerosols suspended in the air. Different atmospheric compositions can subtly alter color balance and intensity, connecting rainbow observations to broader questions about environmental conditions and air quality monitoring. The discovery that rainbows follow universal physical laws while maintaining elements of unpredictability perfectly captures the tension between scientific understanding and natural mystery. We can explain the mechanisms that create these displays, but we cannot always predict when atmospheric conditions will align to produce the gift of a rainbow sighting. Polarization effects in rainbow light encode detailed information about the optical processes occurring within water droplets, creating patterns that can be analyzed to reveal atmospheric conditions and precipitation characteristics. This hidden layer of information demonstrates how much complexity exists within phenomena that appear beautifully simple to casual observation. The geometric perfection of rainbow arcs reflects the mathematical principles underlying natural processes, with each curve following precise relationships between angles, wavelengths, and atmospheric properties. This mathematical elegance reveals how beauty and scientific precision interweave throughout the natural world, creating displays that satisfy both aesthetic and intellectual appreciation. Atmospheric pressure variations create subtle influences on rainbow formation through effects on air density and optical properties, demonstrating how dynamic weather systems affect even the most ephemeral natural phenomena. These pressure effects connect rainbow science to meteorology and atmospheric physics in ways that enhance our understanding of both fields. The formation of multiple rainbow arcs creates spectacular displays where primary and secondary rainbows appear simultaneously with reversed color sequences and different intensities. These complex optical phenomena occur when light undergoes additional reflections within water droplets, producing layered displays of extraordinary beauty and scientific interest. Droplet size distribution determines the sharpness and clarity of rainbow color bands with uniform particle sizes creating crisp, well-defined displays, while variable sizes produce softer, more diffuse transitions. This relationship allows atmospheric scientists to infer precipitation characteristics from careful observation of rainbow properties. The electromagnetic analysis of rainbow spectra provides windows into atmospheric composition and solar radiation characteristics, extending scientific understanding far beyond the visible beauty of these displays into realms of environmental monitoring, atmospheric chemistry, and solar physics research. Thermal effects in the atmosphere create convection patterns that influence water droplet formation and movement, affecting rainbow characteristics in ways that connect these optical phenomena to broader patterns of atmospheric circulation and energy transfer throughout the Earth system. The quantum mechanical nature of light becomes apparent in rainbow formation through wave interference effects that create fine structure in color bands, demonstrating how fundamental physics principles manifest in natural displays we can observe directly with our eyes. Atmospheric dynamics shape rainbow persistence and evolution as changing weather conditions cause these optical phenomena to appear, strengthen, weaken, and disappear, following the rhythms of meteorological systems and atmospheric circulation patterns. The relationship between rainbow observation and human psychology reveals deep connections between natural beauty and emotional well being, suggesting that our aesthetic responses to these displays serve important functions in connecting us to the natural world and providing moments of wonder and renewal. Scientific investigation of rainbow phenomena continues to reveal new layers of complexity and beauty as advancing technology and theoretical understanding provide tools for deeper exploration of atmospheric optics, electromagnetic radiation, and the interactions between light and matter. The mathematical description of rainbow formation demonstrates how elegant equations can capture the essence of natural beauty, revealing the geometric principles and physical relationships that create some of our planet's most stunning visual displays. Atmospheric water in its various forms creates diverse optical phenomena, from liquid droplet rainbows to ice crystal displays, each following different physical principles, but all demonstrating how the same fundamental substance can create spectacular variety in natural light. Shows the persistence of rainbow symbolism across human cultures, suggests something profound about how these displays speak to universal aspects of human experience, connecting us to themes of hope, renewal, promise, and the beauty that emerges from the interaction between earth and sky. Seasonal atmospheric conditions create predictable patterns in rainbow occurrence with certain times of year, providing optimal combinations of weather factors needed for spectacular displays. This seasonal rhythm connects rainbow observations to astronomical cycles and climatic patterns. The study of rainbow formation bridges multiple scientific disciplines, from optics and meteorology to quantum physics and atmospheric chemistry, demonstrating how natural phenomena often require interdisciplinary approaches for complete understanding. Atmospheric turbulence creates dynamic variations in rainbow displays as air motion constantly redistributes water droplets, causing subtle changes in optical geometry that give these phenomena their living, breathing quality. The electromagnetic spectrum extension of rainbow effects into invisible wavelengths reveals the full scope of spectral separation occurring in atmospheric water droplets, providing information about processes that remain hidden from direct human perception. Laboratory studies of controlled rainbow formation have revealed mechanisms and relationships impossible to observe in natural settings, allowing scientists to isolate variables and develop more complete theoretical understanding of atmospheric optical processes. The relationship between background lighting and rainbow visibility demonstrates how environmental conditions affect perception of natural phenomena, with contrast playing crucial roles in determining whether these beautiful displays capture our attention or remain nearly invisible. Particle dynamics in atmospheric water create constantly evolving conditions that ensure no two rainbow experiences are identical, as droplets form, grow, move, and evaporate following complex patterns influenced by temperature, humidity, and air circulation. The geometric relationship between sun angle droplet position and observer location creates precise requirements for rainbow visibility, explaining why these phenomena appear at specific positions and why small changes in viewpoint can dramatically alter the viewing experience. Atmospheric chemistry research using rainbow spectroscopy has advanced understanding of air composition and environmental conditions by analyzing how different atmospheric constituents affect the transmission and scattering of electromagnetic radiation. The quantum mechanical description of light behavior in rainbow formation connects macroscopic beauty to microscopic physics, demonstrating how fundamental principles operating at atomic scales create the large scale phenomena we observe and appreciate. Multiple scattering processes within atmospheric water create complex optical effects that add depth and richness to rainbow displays while encoding information about atmospheric structure and dynamics in ways that connect these beautiful phenomena to meteorological science. The relationship between human vision and rainbow perception reveals how our sensory systems interpret electromagnetic information with individual variations affecting how different people experience these same optical displays. Atmospheric optics. Research using rainbow phenomena has contributed to advances in weather prediction, climate modeling, and environmental monitoring. By improving understanding of how electromagnetic radiation interacts with atmospheric water and particles, the mathematical elegance underlying rainbow geometry demonstrates deep connections between physics, mathematics, and natural beauty, showing how precise relationships create some of nature's most visually stunning phenomena. Atmospheric moisture dynamics involve complex interactions that determine when conditions become optimal for rainbow formation, requiring delicate balances that align only under specific meteorological circumstances. The relationship between rainbow observation and emotional response appears universal across human cultures, suggesting fundamental connections between natural beauty and psychological well being that transcend individual differences. And so, dear gentle listener, we arrive at the quiet close of our luminous journey through the science of rainbows, having traced the path of light as it dances with water, droplets painted mathematical equations across storm clouds, and discovered how electromagnetic waves learn to sing in 7 different colors. We have seen that rainbows are not simply beautiful accidents, but intricate collaborations between physics and atmosphere. Where wavelengths bend at precise angles, droplets act as countless tiny prisms, and geometry creates arcs that span the heavens with mathematical perfection. Yet, for all our scientific understanding, they retain their power to surprise us. appearing suddenly in the aftermath of storms, like nature's own gentle reminder that beauty often emerges from chaos. The next time you find yourself blessed with the sight of a rainbow arcing across your sky, remember that you are witnessing one of the universe's most elegant tutorials in optics, a masterclass in wave mechanics taught by sunlight and written in the language of color. You are seeing light itself, unwrapped like a gift, revealing the hidden spectrum that travels with every golden beam. And perhaps, most wonderfully, you are experiencing something uniquely yours, for no one else can see exactly the same rainbow. The droplets creating your display are different from those creating the rainbow for someone standing just a few steps away, making each sighting a personal conversation between you and the physics of light, a private screening of nature's most spectacular light show. So, whether this gentle exploration has carried you toward sleep or kept you wonderfully awake with curiosity, remember that science does not diminish magic. It simply reveals more layers of wonder. To appreciate the equations that govern rainbow formation are themselves a kind of poetry written in the language of mathematics, expressing truths about light and color that connect us to the fundamental workings of our universe. If you have found peace in this quiet journey through atmospheric optics, I would be ever so grateful if you shared a gentle thumbs up, perhaps subscribed to join our community of curious souls, or simply took a moment to appreciate that you live in a world where sunlight and water droplets conspire to paint temporary masterpieces across the sky. Until we meet again in another corner of scientific wonder, sleep well, dream in all the colors of the spectrum, and remember that somewhere above the clouds, light is always dancing with water, always ready to paint rainbows for anyone fortunate enough to be standing in just the right place at just the right moment when the sun decides to show off its hidden palette. Good night, gentle dreamers. May your rest be as peaceful as mist after rain, and may you always pause to wonder when light bends itself into beauty across your sky.